Good afternoon, everyone, and welcome to EDP and Applied Mathematics Seminar. It's a pleasure for me to open session 19 of this seminar. Today we have two excellent speakers, Nicolas Burq and Maria Soledad Arona. Introducing Nicolas Burq, we have the Professor Marcelo Cavalcanti. Thank you, Marcelo. You can start.
Thank you, everyone. It's my great pleasure to introduce you, Professor Nicolas Burq. Nicolas Burq is an outstanding mathematician around the world. His current position is full professor at the Université Paris Marseille. His PhD advisor was another brilliant mathematician, Gilles Lebeau. Nicolas Burq possesses more than 10 PhD students, at least. He has more than 90 publications in MathSciNet and over 2,070 citations, 2,070 citations. The title of his talk is on the blackboard, Decay Rates for the Kelvin Voigt Damped Wave Equation. Nicolas, the board is yours.
Okay, thank you very much for the invitation. It's a great pleasure to be in Brazil today. Okay, so what I'm going to speak about today is based on joint works with Chen-Min Sun, who is a young guy and it's presently in the University of Cergy. And it will be about a model of damped wave equation. So first I'm going to recall a little bit the classical results about damped wave equation. So all the talk will be about linear equation. There's nothing non-linear, so it's just linear equation. And so it's damped wave equation. So what you do is you do something like that. You work in the domain omega in RD, which is bounded, smooth. You can relax the assumption, but that's not essential at all. And you look at the wave equation in these domains. So it's d2 over dt squared minus Laplace u equal 0. You take boundary conditions. So say for simplicity, u on the boundary of omega is 0. Take Dirichlet boundary condition. You could take Neumann, you could take some other conditions, but it's not the main point here. And you take initial data. U0 is u at time t equals 0, and u1 is dtu at time t equals 0. Okay, and now you add a damping term. A of x dt u. 8 of x times the time derivative of u. Okay, and so for this problem, you have an energy, which is energy of u at time t, which is integral on omega of gradient u square of xt plus dt u square of xt dx. So it's a function of time, and it actually decays. E of u at time t is the energy at time 0 minus the effect of the damping term, integral from 0 to t, and integral on omega of a of x dtu square dx dt. Okay, so it decays. E of u is a decaying function if a is non-negative. Okay, and now the question I want to speak about, or it will not be about this equation actually, so it will be about some modification of this equation, so the main question is, what can you say about the rate of decay? Okay, can you say something about it? So it's a very, very, very classical question. And by now, for this equation exactly, it's pretty well understood. So there are some series of answers. So what can we say? Okay, so first range of answers. So first answer, assume just that A, so A is non-negative and A is not identically 0. Meaning, for example, that integral of an omega of A of x dx is positive. Okay, then you know that the energy always goes to 0 when t tends to infinity. Right, so this is always true. And now, of course, once you have that, you can ask the question, well, okay, I know it goes to 0. Can I say something about the speed at which it decays to 0? So second range of answer, assume that A is positive on an open set. So actually, we could relax to actually no assumption. Now, actually, I can prove the result now. So I am okay. I put this. Okay, this is actually not necessary. Okay, so very recent result in general, but for in the case where you know that it's positive on an open set, then you can say something about the rate of decay, which is the following: the energy of U at time t is smaller. Okay, you can put of course you can 1 times the energy of U at time 0. Of course, this is essentially trivial. I said nothing. The energy is decaying, so it's always bounded by the energy at time 0. But we can also say this: C over log square of t, let's say 2 plus t. And now you put here on the right U0, U1, H2, H1. Okay, so energy, remind you, the energy is like norm of U H1 square plus norm of DTU L2 square. Okay, in some sense. And so what this estimate tells you here, it tells you that if you accept to pay some derivatives, you take some smoother initial data, then you can show that you have, you have a rate of decay, which is at least logarithmic. Okay, so it's something. Well, it's very slow, but still something. Okay, so now, third result, assume that A is positive on omega open set, that omega satisfies what is called geometric control condition. And I will draw a picture of what this condition is. Then it's better. You can put E of U at time t is smaller than E to the minus ct E of U at time 0. So it's exponential decay. Okay, so before explaining the geometric control condition, I'm just going to make a few comments. In general, this trivial estimate is optimal. If you don't put geometric control condition, then you cannot put here better than 1. Of course, I have the energy, So this remark tells you that if I want to put on the right the energy at time 0, in general, I cannot improve 1. If I accept to pay higher norms, I can improve. If I have geometry control, I get exponential decay and energy. Okay, so now just a small picture about what the geometry control condition is. So this is my domain, omega. This is little omega. And geometry control tells you that I take any ray of geometric optics, so the ray reflects on the boundary according to the laws of geometric optics, and then the ray has to enter little omega in finite time. This is geometry control. Okay, I can draw you a picture of a situation where geometric control is not satisfied. Let's take the square. I take a positive little omega, and of course I take this ray here. There are actually many of them. It bounces back and forth and stays forever and never gets into the region where A is positive. Okay, so here, no geometric control. Okay? Okay, so this is the situation where no geometric control, and actually in this case, we can improve a lot this logarithmic factor. So actually in this case, we can prove the following. The energy of U at time t is smaller than C over 1 plus t squared, the energy of U at time 0. In this case, so this is actually a series of results. So it was due to myself, first with Michael Hitwick, and then some results by Anantam and Leoto. Okay, so this shows you in some sense that the rate of decay that you can hope for is very much related to the kind of geometry that you have. So this geometry, in some sense, for the square, there is some instability. Okay. And now that there is a very natural question, which is the following. The question: can I, if I put a stronger damping, do I get a faster decay? Okay, so it's a very natural question. So you see, it's a, you go back, and yes, you go back here, and you look at this equation. Oh, sorry. Yes, better. Okay, so you look at this. Okay, so it tells you that the decay of the energy is driven by the damping term here. So it looks like that if you take R larger and larger, of course, this term will be large. And so we could hope for the fact that if you take R larger and larger, the equation is going to decay faster. Okay, so this is completely false. So the answer to this question is no. And it's very easy to see. You can take A equal constant, and in that case you can compute explicitly the rate of decay. In that case, you look at this equation, so it's dt square minus Laplace u plus a, or I take 2a, just to simplify a little the calculation that I'm going to give you just later. dtu is 0. Okay, and now what I do is I expand u on un of t, en of x. And the functions en are the Laplace eigenfunction with Dirichlet boundary conditions. So you know that there's a Hilbert basis over L2, H1, which is made of this eigenfunction. So En is a Hilbert basis of L2, and En over lambda n is a Hilbert basis of H10 of omega. Okay, so I can expand my solution on this, and now I can compute because I have I just put this and that in the equation, and I just get a very simple equation for un. Of course, if I compute, I just get un, or maybe I take this, un second 2 time derivative of t plus lambda n square un. Okay, so this is lambda n square un is for the action of Laplace un. Laplace applied to en gives you lambda n square. And again, I have plus, let's get 2a u prime n of t equals 0. Okay, so now I can solve this equation. Of course, the characteristic polynomial for this equation is just x squared plus lambda n squared plus 2ax equals 0. And now you have two roots of this second order polynomial, which is x equal, well, xn plus or minus. You have two roots, and I'll solve my equation, and I have xn plus or minus is minus a plus or minus square root of a squared minus lambda n squared, if a is larger than lambda n, and it's minus a plus or minus I square root of lambda n squared minus a squared, if a is smaller than lambda n. Okay? And now I stop a little bit and I think, and I want to understand what happens if I take larger and larger damping. So I take a going to infinity. So question, damping a goes to infinity. I want to understand the decay. So of course, if I go back to my solution, I have my two roots here. And so I can solve this equation. And I have un of t is e to the xn plus t times alpha n plus beta, or let's call it, plus alpha n minus e to the xn minus t. Right? And so the rate of decay of my solution is given by, so rate of decay given by the real part of xn plus and the real part of xn minus. Of course, the real part is always negative. Simply, I just look at my solution, and the real part is always, the real part here is always negative, because here, and I always have something, because you see here, lambda n is always positive. We call lambda n is positive. Okay? And so the worst rate of decay is given by the smallest real part. And I just check. So which one is it? Yes, you can check this one. And the worst part will be, so worst part will be minus a plus square root of a square minus the smallest eigenfunction. Okay? And now, of course, this is minus a plus a times 1 minus lambda 1 square over a square to the 1/2. And so it's essentially minus a plus a minus lambda 1 square over a. Okay? And so that shows you that when a goes to infinity, the rate of decay becomes worse and worse. It's completely counter to the intuition. It's too much decay, too much damping kills the damping in some sense. So if you look at what will happen, actually it will be the best rate will be given essentially, it will be written in terms of the first eigenvalue here, lambda 1 square. Okay, but this shows you that it's not true that if you take larger a, the decay will be faster. So what will happen is something like that. If I draw the picture, I take in terms of, oh, sorry. If I draw the picture, so this is A. For A equals 0, I have no damping. And now the damping will increase first, and then essentially it will decay. Okay, so this is rate of exponential decay. Something like that. So there is a best A, which is somewhere here. Okay, and we can compute everything. Okay. Okay, so now I play up. Sorry. Yes, here. Oh. It's okay? No. Is it okay? I don't know what happened. Can you see me, hear me? I don't know what happened.
Yes.
Okay, I don't know what happened to my, okay, maybe I absolutely don't know what happened. So I got disconnected, or maybe I was not disconnected at all. Okay. Let's do it again. Yes. Okay. Okay, I go back. So, okay.
Okay.
Okay, so this just very simple calculation shows you that even for the damped wave equation, the classical one here, you can get into trouble if you want to take too large dampings. Well, it's not big trouble, but it's just the fact that you'll not get so good decay. Okay, so now I'm going to play a slightly different game. I take a much larger decay, a much larger damping term. So now what I do is it's just the following. I switch my equation, so it's dt squared minus Laplace, same as before, u. And instead of a dtu, I'm going to take minus the divergence of a of x gradient x dtu. And all the rest is the same, okay? So in some sense, I changed so what I did is I didn't take a go to infinity, but I add some derivatives here, divergence and gradient. And so in some sense, I'm taking a much stronger decay. Okay, so and now you can just play the same game, and you also have an energy u at time t, which is E of u at time 0 minus integral 0 to t, integral and omega. And now what I'll get is a of x gradient dtu square dx dt. So instead of dtu, here I have gradient dtu, so something which is larger. So it's not a that is larger, it's this term that is larger now. Okay, and now I ask exactly the same question. Can I say something about the rate of decay? And in some sense, if you think about what I just showed you, you can think that it will not always be better. And so question, rate of decay, is it better or worse than previously? Okay, so there are many contributions about this one, so I'm just going to write a few names, but there are, of course, many other persons. So in particular, so there's some results by Zhang, by Tebu, and by Webe, Nasser, Noon, particular, but plus many others. Okay, so what I'm going to do just now is same thing. What can we do about that? So first result, same thing. If A is not identically 0, then the energy at time t goes to 0. And actually, you can do better. You get exactly the same result as before. Is smaller than c over log square of 2 plus t, provided you take u0, u1, h2, h1 square. It's exactly the same thing as before. So now it's just the result telling you, okay, for this general result, it's the same as before. Nothing new, not worse, not better. Logarithmic decay. Now, where things become interesting is assume that the set where A is positive satisfies is open, plus the geometric control condition. And now the question is, well, is it worse or better? And now the answer is, well, it depends. If A is smooth, you also get exponential decay. No. Theorem. So it's due to myself with Christensen and Sun. So if A is, say, C2 on omega, then the energy of you at time t is smaller than C e to the minus Ct, the energy at time 0. Okay? Now, theorem, this one is due to Zhang and so if A is, say, for example, the characteristic function of a domain, then it's much worse than previously. Even if omega satisfies geometric control, well, you just have something like that. Okay, so what is it exactly? I think it's t squared. Yes. Okay. And this is optimal. You cannot improve. Well, there are some examples of domains where we can prove that we cannot improve. Right, so we can exhibit some examples. It's really we cannot. So this is, so you see it's a little bizarre argument telling you, okay, if A is smooth, nothing new, exactly as in the previous case. But if A is not smooth, then it can be much worse. And so it's actually, maybe I'm going to explain a little bit how things work. It's because I don't have so much time. So what will happen is the following. You have your domain, and you have A positive, and you're going to play exactly the same game. You're going to propagate the energy. Okay. And now I stop, and the phenomenon will depend on whether A is smooth or not. So if A is the characteristic function of a domain, so you have a step function, so it's 0. So say A equals 0 and A equals 1 here in this domain. What will happen is this. When the energy comes here, it will bounce. And again, and bounce again. And each time, here and here, very little energy will be dissipated. Because you have a step which is too high. So the wave cannot enter the region where where you have the damping. You have a solid wall which is too high, and so the wave is going to bounce on this wall. And still a little bit of dissipation here and here each time you hit the boundary. So this little bit of dissipation will be responsible for this rather slow decay. The dissipation is not 0, so you have a decay, but it's not a big dissipation enough to get a very fast decay. So now what happens in the case of a smooth damping? So let's say A is positive. Now A is C2. So it means that if I draw a picture at the point where, so if I draw a picture of the graph of A, this is X, so at the point where A, so let's say, for example, A equals 0, you have a reasonably smooth junction here. So it's C2. You have junction here. Okay, and so that means that I go back, I propagate same picture, but now the situation will be different because when my wave arrives here at the interface, you don't have this solid wall. So previously, you had a wall like that. And so my wave, which was arriving here, cannot enter the region where it will be dissipated, and so it bounces back. Here, the picture is different. My wave arrives here, it enters a small boundary layer, and it's completely absorbed. Nothing is bounced back. Wave arrives here, and that's the end of the story. At total absorption. Yeah. Here. Weak absorption. It would be. Okay. So this phenomenon is going to explain you the huge difference here and here. So in some sense, this corresponds to the case where you have a very, very large A and your wave is very little absorbed, very little length. This case corresponds here to the fact that your wave, at the beginning, what the wave C of A is very small parts of A, because at the interface, A is going to be very small. You see, just on the boundary, since A is smooth, here, A is large because it's not smooth, but here in this picture, at the boundary, A is small because A is C2. Okay, so this is what happens heuristically. And now, of course, if I just have I just have a couple of minutes, and in terms of mathematics, you have to work. So what you have to do is so the program is work with resolvent estimate. And then you have to understand some coupled systems of partial differential equations, and the main difficulty is that these couples are the systems are boundary value problems. Okay, so that means that you need to do microlocal analysis for boundary value problems. So this is actually rather technical. Okay, but at the end of the day, you can prove exactly the heuristic. Okay, and so now just a remark to finish the talk is that I said that this rate of decay is optimal, and so it's actually not completely true. The rate of decay is optimal for d larger than 2. For d equal 1, you can improve this 2 to a 4. And so you need to understand why, and I can draw you a picture of a domain for which I can show that we cannot improve. So I take any domain here, it doesn't matter. And now I put in the interior, so it's true for a circle or an ellipse. So a equal 1, a equals 0 everywhere. And in that case, I can show that, so if I have E of U of t smaller than c over 1 plus t squared times u0, u1, h2 times h1 square, and in that case is optimal for this picture. So this is circle or an ellipse. Let's use some special geometrical properties of the domain where I can construct some special functions in this domain. Okay, so maybe I think it's time I stop my talk here. Thank you very much for your attention.
Thank you very much, Nicolas, for your nice talk. Now I have that to do if you have some questions or comments to Nicolas. Any questions or comments?
I have any question. Good morning or good afternoon. I have some question.
Yes.
My question is, do you work this problem with exact solution? I would like to know exact solution. When you solve the partial differential equation, how is the estimative? How is it? I would like to know
How we solve the equations. So okay, so to solve the equation, it's actually very easy. So it's very easy. It's really a complete standard notion of solution. So it's the solutions. You write the system in terms of dt. So you write u is u and dtu. And you write the second order equation as a first order system on big U. So u equal, so it will be 0, 1, and I have Laplace, and I have, I don't know, the divergence a gradient, something like that. U. And so this is an operator AU, and it just falls into the Hill and Yoshida semigroup theory. So you just have to show that A is maximal dissipative. And of course, this is because A is positive, not negative. You see, there's actually, it's an interesting question. So there's actually a difference between, if I go back to the first model for the usually damped wave equation. Yes, here, for this model, to solve the equation, you can assume that A is positive or A is negative or A is any. It doesn't matter. You can solve the equation in both cases. You can solve the equation toward positive t, or you can solve the equation backward toward negative t. For the other model with the Kelvin Voigt damping rate, this one, okay, it's no more true. For this equation, you cannot just solve the equation from 0 to positive t. The equation is not reversible. And you see it in my picture. I said here, the energy is completely absorbed. If you have complete absorption, it really means that you cannot solve the equation backward, because starting from 0, you would create something. So the equation, in terms of Yoshida, is just well posed. So well posed from t equals 0 to t positive, and not backward. It's not well posed from t equals 0 to t negative. We cannot solve the equation backward. Okay, but apart from that, it's really just a semi-group equation. So it's elliptic estimate. So it's two integration by parts, and you've proved that the equation is well posed. It's not difficult.
Okay, thank you. Anything again? Thank you very much. Thank you.
Okay, do you have another question to Burq? Nicolas, I have a question. The condition used by Thébault that according to the range of A, square is less than a constant plus A. Did you remove this hypothesis?
I'm sorry, I didn't hear the question.
To have a Thébault, he assumed that the gradient of A modulus square less than a constant, a square is less or equal to a constant. It is less than a constant plus A.
Okay, so yes, so the only so we don't need A in C2 actually. So what we have is what we need is this estimate. Is the fact that the gradient of A has to be smaller than a constant A to the 1/2.
Yes.
Okay.
Okay.
And it's an exercise of calculus to show that this is true when A is C2 in omega.
Oh.
It's just so you can go and check. We wrote it in our paper. It's just a consequence of how do you call this Taylor-Lagrange formula.
Okay, thank you very much.
Right. So actually, so I wrote the result for A in C2, but it's actually true under this weaker assumption. We just need one derivative.
Mm-hmm.
Yes, and so I should have said that. I should have. It's a good remark that for this case we should have Thébault also. You have some not general in terms of geometric control, but he had some partial results in this direction.
Other question or comment to Nicolas? Now let's thank Nicolas again. Thank you very much, Nicolas, for his nice talk.
Thank you for the invitation.